In this video, we're going to be taking a look at a charged particle between charged plates. Now, the first one, we're going to solve for the velocity of an electron between these two plates with their respective voltages. And for our second one, we're going to take a look at this one with the electric field and a separation distance, and we're going to do multiple different methods to solve for that velocity as well. So for this problem, we have an electric field that points from left to right from the positive to negative, but since we have an electron, it goes the exact opposite direction of the field because it gets repelled by the negative plate and attracts towards the positive plate. Now, with that being said, we can find the work done by the electric field, which is Q times delta V. So let's go ahead and plug in those values because we know the Q and the M. We can use those to our advantage because those are constants for an electron and a proton as well, which we'll eventually use for our second problem over here. So let's go ahead and plug these in and see what we get for work. Now for this one, I just took the magnitude of the charge for an electron, so there's no negative in front of it. And then I took the delta V. Here's the ending voltage of 150 minus the initial. So we're subtracting the negative 50, which makes it 200 volts as the delta V. Now the work done by the field is 3.2 times 10 to the negative 17th joules. Now the rule is that if the field is causing something to accelerate and gain kinetic energy, and then it's a positive value for work. So for an electron, if it's moving against the field, that's its natural way to move. That gives it kinetic energy, then the work is positive, and vice versa for a positive charge. Now, all of that energy added into the electron by the electric field is all going to be converted into kinetic energy. So we can go ahead and say that the 3.2 times 10 to the negative 17th joules is getting all converted to kinetic energy, which we know is 1/2 mv squared. 9.1 times 10 to the negative 31st is our mass of an electron. So what we can do is we can go ahead and divide both sides by half the mass because this is going to have the mass. So that's going to be 4.55 times 10 to the negative 31st. And then we will end up square rooting both sides to take care of that squared value. And then that leaves us with a velocity of 8.39 times 10 to the 6th meters per second. So a lot of times when you're talking about charged particles that are getting accelerated, because of their really small mass, they'll tend to have a really large acceleration and have really, really high velocities. So that concludes our first problem. Now for our second problem, we're going to take a different approach because we have a distance and an electric field. So we have some different things to work with. So this right here is our electric field. The electric field goes from left to right, from the positive to negative. Because it's a proton, it does actually follow these field lines and go from left to right. Now, if we're finding the velocity of this proton, we can do it a couple different ways. So the first way I'm going to use is I'm going to go ahead and use Newton's second law, where the acceleration equals the force over the mass. And then if we're looking at an electric field, for the force, we can get that by doing Q times E, the charge of the electron times the electric field. And just like the electron, we know the charge and the mass of a proton. Those are known constant values. So let's go ahead and plug those in and solve for acceleration first. All right, now that we found that acceleration, we can use that with some kinematic formulas in order to find our velocity. So how we're going to do that is anytime we use an kinematic formula, we have to have three different known variables. So we have the acceleration, so that's 1, obviously. And then 2, we have the distance of 20 centimeters. If we divide that by 100, that's going to be 0.2 meters. And then also we know that if it's held up against this plate, we could say it starts at rest with an initial velocity of 0. So that would be enough to go ahead and use this formula. Vf squared equals Vi squared plus 2a delta x. Okay, that is one of the acceleration formulas that's not dependent on time, and we don't have that, so that's good. So let's go ahead and plug in these values and see what we get. So this one ended up working out pretty nicely. We just had to find the product of these three numbers, our acceleration with the coefficient of 2, and then our delta x, and then the 0 just going to drop out. So just basically finding the square root of both sides. And then we have our velocity. Now, we could also solve this one other way as well, because we know the electric field and the separation distance. We can also work with those as well to find it using a different method. Now, if you want to use the energy method, then we're going to find the work by finding the product of Q, E, and D. And then just like the previous one, the work done by the electric field is going to give it all of that kinetic energy. So we can go ahead and set that equal to 1/2 mv squared. And we do know all of those things based on what we're given initially in the problem. So let's go ahead and plug those in and see what we get. All right, now I found the value for work with the Q of a proton, which is the same as the electron, except it's positive, times the 2000 newtons per coulomb for the electric field, times the separation distance equals 1/2 m, the mass that we used earlier for the mass of a proton, and then basically just found this number, divided both sides by it, and then square rooted it. And due to some rounding, my number is a little bit off, 276,851 meters per second. I believe I didn't keep all of the digits in the calculator, so once I plugged it in, the velocities came out slightly different. Either way, both methods are basically different approaches to finding the same sort of thing. So depending on what you're more comfortable with or what works more intuitively for you, you can find the velocity both of those ways. So I hope that was helpful to you in solving for the velocity of a charged particle between some charged plates. Thanks for watching and listening.